Okay, so now let's try to find the magnetic field produced by an infinitely long wire that carries current I. So here's the infinitely long wire, so there's current going through here, which is, let's say, I naught. We want to find the magnetic field of this current, and so the current this continues on all the way down to infinity, and the current is flowing that way, and there's a uniform current I naught through the wire. Okay, so we want to find the magnetic field everywhere in space. So say we pick a point and we look at a little piece of the infinitely long wire that has a little distance dr, and that's labeled with dr arrow because there's a direction, and there's a current going through there. There's a little bit of current through there, and we are at some distance from the point, which is r. Right? We know that the magnetic field decreases as 1 over r squared, and our expression for the magnetic field is given by something we found or that we imagined finding experimentally. Right? It's some constant, mu naught over 4 pi, times the integral of I, in this case it's I naught, dl or dr, rather, I labeled it as dr, so this would be a dr cross r hat over r squared. So it's that kind of a quantity that we have to figure out how to evaluate. So let's first recognize that we need to deal with the cross product there of dl cross r hat. So we have, or dr, sometimes it's called dl, dr or dl, same thing. So we have dr cross r hat. We have to take everything in this expression and write it as a function of the variable of integration. So we're integrating from minus infinity there all the contributions of these little pieces along the wire. They create a magnetic field here, and the distances are, it goes to infinity down there, and it's changing, and so all these little pieces are at different distances from this point, and we need their net contribution to the magnetic field. So the first bit is dl cross r hat, and so we could say that we are, let's choose coordinates such that, say that this is y and this is x. Okay, so then we would be integrating in y. So the integral would be a dy integral. And so dl in magnitude is a little tiny bit of distance it's an infinitesimal distance in the y direction, so that becomes a dy. Right, so in terms of this quantity, we can write it as the magnitude of dr times the magnitude of r hat times the sine of the angle between these two times some unit vector. So we have dy, and let's call this angle phi. So we have dy times the magnitude of this unit vector, right? So the unit vector r hat is pointing that way, so the r hat is that way. Sorry, r hat, not r. dr is pointing this way, right? So dr, I labeled it already there, but it's pointing upward along the y, and r hat is pointing to where we want to evaluate the field, and so phi is the angle there. And so that angle depends on the value of y, right? So if we're further up along here, then the y value is greater, and comes into play in figuring out the distance r, right? So this is given our coordinates. This is an x distance, that's not changing, but the y distance is changing, and then we have Pythagoras' theorem that applies there. So we can write everything in terms of y. The magnitude of the unit vector is 1, so we have dy sine of phi, which we need to evaluate in terms of y. And then we can do the right-hand rule to figure out the unit vector here. So it's dr cross the middle finger is r hat to where we want to know the field. It's hard to show it here. It's with my right hand, it's like that. My middle finger has to point not at 90 degrees, but a little bit further. This is larger than 90 degrees, so my middle finger is pointing that way. And the resulting vector, the thumb, is pointing into the page. And so that would be a minus, the minus z direction, so we could say minus k hat. Minus k hat for that. And so we've written part of this in terms of y. And so let's continue figuring out how to get this in terms of y. We have dy, but the angle phi, right? So if we think of this as the x value, this is the y value, then this angle here is related to phi. We can call that theta, and that will give us something that we can figure out that in terms of x and y. Let's see what do we get here? So we get the sine. The sine of phi is also the sine of 180 minus theta, right? So this angle phi is 180 minus theta. So now we've written sine of phi in terms of theta, and we still have the minus k hat, and therefore we end up with a dy. Given the property of the sine of pi minus theta is the same thing as the sine of theta itself. And so we end up here and so what does our expression look like? Well, now we have dy, and we can figure out the sine, right? The sine of the angle is by definition the opposite over the hypotenuse, and the opposite involves the x value. So this is whatever the x coordinate is, and the hypotenuse is this, but the hypotenuse involves the y value. Right, so if this is our origin, then this is our y value, and this is our x value, and this is, of course, x squared plus y squared square root. So sine of theta becomes the opposite, which is x, over the hypotenuse, which is x squared plus y squared square root. And now we've written the sine of theta in terms of the variable of integration y, which we needed to do. And of course, we still have the minus k hat. So we now have, let's see, we can write the entire expression out as, let's see, b is now equal to mu naught over 4 pi times the integral. I naught is just a constant, right? It's uniform everywhere, so we can just pull that out. We're integrating from minus some y equals minus infinity to plus infinity. And our expression now is x over, let's see, x squared plus y squared. But we have the r squared in here, and that's x squared plus y squared. So unsurprisingly, we'll get what we've seen before for the electric field, x squared plus y squared to the 3 halves. And this is in dy times minus k hat. So now we have to evaluate that expression.